Okay, good morning everyone. In the last class, we have discussed two classic problems of process synchronization, and we tried to solve those two problems. One is bounded buffer, which is also known as producer consumer problem, and second was readers writers problem, and we tried to solve both of these problems with the help of semaphores. And in today's class, we will talk about the third and the last classic problem of process synchronization, which is known as dining philosopher's problem. And we will see what is the problem and what is the solution to this specific problem with the help of semaphores. So just before starting, let's try to understand what is this dining philosopher's problem, what we have to do exactly, and what are the various possible solutions. So, as the name suggests, dining philosophers. So, in this particular problem, we have a circular shaped dining table surrounded by five different chairs, and each chair is reserved for a philosopher. So, in the center of that dining table, we have a rice bowl, and philosophers usually spend their lives either by thinking or by eating. So, they have two tasks in this particular problem: either they think, and whenever they get tired of thinking, they just eat. So you can see there are five different chairs and a circular shaped dining table, and there is a rice bowl in the center, and there are plates in the front of each philosopher, as well as there are some chopsticks. So five philosophers and five chopsticks are there, with the help of which the philosophers will eat the rice whenever it is required. Now, there are some specific rules how and when the philosophers will be able to eat the rice. So, there are some predefined rules. So, we have to remember that. So, whenever any philosopher get tired of thinking, he or she will just simply eat the rice. But for eating the rice, the philosophers requires two chopsticks. So two nearest chopsticks the philosopher will pick, and only after that the philosopher will be able to eat the rice. But there are some conditions. So very first condition is that a philosopher can pick only one chopstick at a time. So एक time में एक philosopher एक ही chopstick को pick कर सकता है. Second is there is a specific order of picking a chopstick, so that will be applicable for all the philosophers. So if any philosopher want to eat the rice, so first of all the philosopher will pick the chopstick, the left chopstick at a time, and after that that philosopher will pick the right chopstick. Then only he will eat the rice, and after eating in the same order he will put the chopstick back. First of all he will put the left chopstick back to the dining table, and again the right chopstick will be put after the left chopstick onto the dining table. So this will remain the scenario, and we will see the problem deals with how many philosophers will be able to eat simultaneously if all of them are hungry, or if at least any two consecutive philosophers are hungry, or if any two alternative philosophers are hungry. So this is all about the problem. I hope the concept is clear to you. So this eating is a critical section here because we will see how many philosophers at a time will be able to eat, and this thinking will act as a remainder section here. So philosophers spend their lives thinking and eating, and they do not interact with their neighbors. So they cannot take the chopsticks from their neighbors. They will only pick it from the dining table only. So if it is available, then they will pick, and if it is not available, then they will definitely wait for the chopsticks. So they do not interact with their neighbors, and they occasionally try to pick up two closest chopsticks. So closest chopsticks means, first of all, any philosopher will pick left chopstick at a time, after that right chopstick at a time, and then he will start eating the rice. And whenever the eating is done, so need both the chopsticks to eat and then release both the chopsticks in the same order, first left, then right. And after that, the philosopher will start thinking again. That means it will enter into the remainder section. And if we consider, so this problem can be generalized for as many as philosophers, but we have to be careful that the number of philosophers and the number of chopsticks will always remain same. So in the dining table, if there are 7 philosophers, then there are 7 chopsticks. And we are just considering the case of 5 philosophers. So there are 5 different philosophers and there are 5 different chopsticks which are available. And there is a rice bowl in the center of the dining table. So if we talk about the 5 philosophers, the shared data will be the bowl of rice, which we can assume as a data set. And to solve this dining philosophers problem, we will take an array of semaphores with the name chopstick, and we will take as many semaphores as many chopsticks we are having, and all of the semaphores, as we already know that in the case of critical section problem, we always initialize these semaphores with 1 always, and these will be the binary semaphores. So in this particular case, we are having 5 chopsticks, so we will take an array of semaphores with the name chopstick, and we will take the 5 semaphores also. So if we move to the code, so this is the code for the critical section problem, or in the case of dining philosopher algorithm. So this is the general structure for any philosopher I. So if we have 5 different philosophers, suppose from P0 to P4, and if we talk about the general structure of any philosopher, so it will be something like this. So weight of chopstick, that means if we are talking about philosopher 0, then philosopher 0 will pick the left chopstick first. So you can see this is I. So if I is 0, then the philosopher will decrement the value of chopstick of 0 and chopstick of 1. So that means we will arrange the chopsticks in such a manner that the index of this philosopher, the index I, will be the same index as of the left chopstick, and I plus 1 will be always be the right chopstick of the philosopher. And after performing these 2 operations, the philosopher will be able to have both the chopsticks, and philosopher will start eating the rice. And whenever he is done, he will just simply put the left chopstick first, then right chopstick, and it will enter into the remainder section. So this is what the problem is. So this is the general structure, and just let me share the board to explain it more precisely for all of you. Okay, so I hope the board is visible to all of you, and you can see this is the general structure of the dining philosopher problem. This is the code which I have just shown you in the slides, and this specific diagram represents the dining philosopher problem. We have a circular shaped dining table. In the center we are having a rice bowl. Now just see carefully here, we have 5 different philosophers, P0, P1, P2, P3 and P4, and we have 5 different chopsticks which are represented in the blue color. So this is chopstick C0, C1, C2, C3 and C4. So the overall scenario is, if philosopher P0 wants to eat the rice, so P0 requires these 2 chopsticks, and the order is also fixed. So first of all, P0 will always pick C0, and after that P0 will pick C1, and when P0 will have both C0 and C1, then only he will be able to eat the rice. Similarly, if I talk about philosopher P1, so P1 requires C1 first, then C2, then only philosopher P1 will be able to eat the rice. So this is the scenario. That means if I talk about philosopher P0, so P0 requires 2 different chopsticks, that is C0 and C1, And if I talk about philosopher P1, so philosopher P1 also requires two chopsticks, that is C1 and C2. Similarly, philosopher P2 requires two chopsticks, one जो उसके left में होगी, so this is the left of the philosopher P2 because all are directing towards the center of the table. So P2 का left C2 and the right chopstick of philosopher P2 is C3. So when this will remain the scenario for all the philosopher. So किसी भी philosopher को अगर rice eat करने हैं, so first of all that philosopher will pick the left chopstick first, after that right chopsticks, and if he is having both the chopsticks, then only he will be able to eat the rice. And you can just simply relate, we have made this diagram something like that the index is already matching in this particular case. So for P0, C0 and C1 is required. So you can just see P0, the left chopstick of this philosopher is C0, right is C1. And if I talk about P2 suppose, so for P2, these two chopsticks C2 and C3 is required, and you can check this is P2 which is sitting something like this, so the left chopstick is C2, then it is C3. Now if suppose first of all only philosopher P0 come, so what P0 will do, we will use the concept of semaphores here. We will have 5 different semaphores and we will have chopstick, or we can say suppose semaphores S0, S1, S2, S3 and S4. So जितने भी हमारे पास number of chopsticks होंगे हम उतने ही semaphores लेंगे इस dynamic philosopher problem को solve करने के लिए, and all semaphores will be initialized to 1. So initially the values, assuming the simplest case where at a time only one philosopher will come and it will execute the code of entry section, then it will eat, then it will just exit the critical section and it will enter the remainder section. So अगर मैं philosopher P0 की बात करूँ, so philosopher P0 को ये वाला कोड एग्जीक्यूट करना है क्या करने के लिए, क्रिटिकल सेक्शन में एंटर होने के लिए या फिर बोले राइस को ईट करने के लिए. So initially all the semaphores are initialized with 1. So this is the code which any philosopher will execute if the philosopher wants to eat the rice with the help of both the chopsticks. So what it will do, it will just simply apply the weight operation on chopstick I. So P0 की बात कर रहे हैं, so that means the value of I is 0. Because जो भी इंडेक्स है फिलोसोफर का वही हमारा चॉपस्टिक का इंडेक्स रहेगा. सो दैट मींस P0 फिलोसोफर को C0 एंड C1 चॉपस्टिक की रिक्वायरमेंट है, एंड फॉर C0 चॉपस्टिक वी हैव अ सेमाफोर S0, फॉर C1 चॉपस्टिक वी हैव अ सेमाफोर S1. सो व्हाट फिलोसोफर P0 हैज टू डू, P0 हैज टू apply the weight operation. So weight means it will just simply decrement the value of the semaphore weight chopstick of 0. So chopstick की जगह मैंने यहाँ पे S ले लिया है, so you can just replace it with S also. So that is one and the same thing. So what P0 will do, P0 will apply weight on it, and P0 will apply weight on chopstick I plus 1 mode 5. So P0 I की वैल्यू 0 है, so 0 plus 1 1. 1 mode 5 will be 1. So that means we are talking about C1. For C1 we have S1. So initially what philosopher P0 will do, it will just decrement the value of these two semaphores S0 and S1 from 1 to 0, and by doing this philosopher P0 will be able to enter the critical section. It will be able to eat the rice because philosopher P0 के पास अब दोनों chopsticks C0 और C1 आ गई हैं जिसकी उसे requirement थी. And once philosopher P0 is done with eating, what it will do, it will just simply again apply the signal operation on both the chopstick. For P0 it will be chopstick of 0 and chopstick of 1. So after eating it will just again update its value, increment it by 1, and it will just exit the critical section and it will again start thinking. So this is the simplest case you can see where one philosopher wants to eat the rice and there isn't any problem. Now let us discuss another important case. While philosopher P0 was eating the rice, and at the same time, suppose philosopher P1 also wants to eat. So initially, all the semaphores are initialized by 1, and if I talk about philosopher P0, so P0 requires C0 and C1. So simply it will just update the values of S0 and S1 to 0, and P0 will be able to enter the critical section, or philosopher P0 will start eating. Now P0 is still eating, and now philosopher P1 also wants to eat something, eat rice. So what P1 has to do? So P1 requires these two chopsticks which are on the left and right. So first of all, P1 will pick C1, then it will pick C2. But for C1, philosopher P1 को क्या करना है? It has to weight chopstick of 1. So chopstick of 1 पे weight apply करने की, that means S1 पे weight apply करने की try करेंगे, लेकिन already P0 philosopher is S1 semaphore की value को 1 से 0 कर चुका है. So that means P1 philosopher will not be able to have this C1 chopstick, because C1 chopstick is already अभी किसके पास है? P0 philosopher उसको use कर रहा है. So that means if philosopher P0 is eating, then the philosopher which is sitting next to this philosopher P0 will not be able to have this C1, because P0 is already using these two chopsticks. But there will be any problem if at the same time philosopher P2 wants to eat rice? So let us discuss that case also. So I am assuming the same case. P0 सबसे पहले आया, P0 ने C0 और C1 की रिक्वायरमेंट थी P0 को, उसने S0 और S1 को वैल्यूज को 1 से डिक्रीमेंट किया, एंड P0 is eating. Now at the same time, let's suppose P2 wants to eat also. So philosopher P2 wants to eat. So here is P2 requires C2 and C3. तो भाई P2 को क्या रिक्वायरमेंट है? C2 chopstick की and C3 chopstick की. This is the condition. So if I talk about P2 will also execute the same code. Now the index of this philosopher is 2. That means it will apply the weight operation on chopstick 2 and chopstick 3. So chopstick 2 के लिए हमारे पास S2 है. So S2 की वैल्यू को 1 से 0 करेगा, S3 की वैल्यू को 1 से 0 करेगा. And now you can see there will not be any problem. P0 and P2 both will be able to enter the critical section, or both will be able to eat the rice at the same time. Now you can see in the case of critical section problem, we always have the concept of mutual exclusion, but this is the exceptional case. This is the exceptional classical problem where at the same time more than two philosophers can eat the rice together. But यहाँ हमारे पास एक condition है, वो alternate philosopher होने चाहिए, वो continuously जो साथ बैठे हुए वो वाले philosopher नहीं होने चाहिए. So you can easily see, अगर हमारे पास philosopher P2 critical section में है या philosopher P2 eat कर रहा है, तो P2 के पास कौन-कौन से दो chopsticks हैं? C2 and C3. That means अगर P3 भी same time पर critical section में enter होना चाहेगा, P3 also wants to eat rice at the same time, P3 will not be able to enter because P3 also requires C3, but C3 already कौन use कर रहा है अभी? Philosopher P2. So this is the entire scenario. That means अगर P0 eat कर रहा है at that time, P2 enter कर सकता है, there will not be any problem. Why? P0 को क्या requirement है? C0 and C1 की. P2 को क्या requirement है? C2 and C3 की. So they are not related with each other. They are not dependent on each other. Similarly, अगर हम बात करें P1 and P4 की, so P1 requires C1 and C2, these two chopsticks, and P4 requires C4 and C0, these two chopsticks. So there isn't any connection between these two philosophers and their chopsticks. So definitely they will be able to enter the क्रिटिकल सेक्शन. नाउ अगर हम बात कर रहे थे P2 है और P3 नहीं एंटर कर पाएगा, बट सपोज P2 is done with eating, so when P2 क्या करेगा, P2 will execute this particular code. It will again change the value of S2 and S3 from 0 to 1, and now process P3, philosopher P3 will definitely be able to enter the critical section because P3 requires C3 and C4, so it will just decrement it from 1 to 0 and successfully it will be able to enter. So this is the overall issue, this is the overall problem, and I hope the concept is very much clear. So this is very easy code. जिस भी philosopher को eating section में जाना है, critical section में enter होना है, it just have to decrement the value. It has to apply the weight operation on its left chopstick and its right chopstick, and similar is the procedure if any philosopher wants to exit the critical section, or if he or she is done with eating, they can just simply increment the value of their left chopstick and right chopstick semaphore by 1. So this is how the entire scenario will work, and I hope the concept and the problem is very much clear to you. So as you can see, collectively एक साथ सारे के सारे philosophers ईट नहीं कर सकते. इवन टू कंसेक्यूटिव P0 है तो P1 नहीं ईट कर पाएगा, P3 अगर ईटिंग सेक्शन में है तो P4 भी ईट नहीं कर पाएगा. सो देयर आर सम डिफरेंट सॉल्यूशंस. क्या क्या पॉसिबिलिटीज हैं दैट वी विल डिस्कस, एंड जस्ट बिफोर डिस्कसिंग दैट आई एम जस्ट डिस्कसिंग one major problem which may occur in the case of this dynamic philosopher problem, and that is known as the problem, the deadlock problem. So just let's assume initially all the semaphores are initialized with 1. So as we know that philosopher P0, if it wants to enter the critical section, it requires two chopsticks C0 and C1. Similarly, philosopher P1 requires C1 and C2. Philosopher P2 requires C2 and C3. Philosopher P3 requires C3 and C4. And philosopher P4, the last philosopher, it requires C4 and C0. These two chopsticks to eat. Now, in the case of dynamic philosopher's problem, we might have a problem which is known as deadlock. So, कैसे होगा deadlock? So, just let's discuss that. So, let's suppose one by one इसी order में हमारे पास philosophers आए, those who want to enter the critical section or those who want to eat the rice. So, suppose first of all, philosopher P0 come, and to enter the critical section, philosopher P0 will execute this particular code. So just assume philosopher P0 ने first statement weight of chopstick I, यानी कि लेफ्ट वाले जो चॉपस्टिक थी C0 उसको पिक किया, उसकी वैल्यू को 0 किया, और जैसे ही वो नेक्स्ट स्टेटमेंट को एग्जीक्यूट करने लगा वेट ऑफ चॉपस्टिक I + 1 mod 5, वो उसी टाइम पर हमारा फिलोसोफर P1 आ गया और P0 प्रीएम्प्ट हो गया ड्यू टू एनी रीजन, एंड फिलोसोफर P0 के पास सिर्फ लेफ्ट वाला फॉर्क है, लेफ्ट वाली चॉपस्टिक है, दैट इज C0. नाउ P1 will again execute same code, and first of all P1 will pick the left chopstick. So P1 ने जैसे ही C1 वाली चॉपस्टिक यानी कि अपने लेफ्ट हैंड साइड वाली चॉपस्टिक को पिक किया, P1 also got preempted and P2 comes. So दोनों philosophers के पास अपने लेफ्ट हैंड साइड वाली चॉपस्टिक है, बट जैसे ही वो राइट वाले चॉपस्टिक को पिक करने लगते हैं वो साथ के साथ प्रीएम्प्ट हो जाते हैं. सेम इज द केस विद फिलोसोफर P2. P2 ने फर्स्ट स्टेटमेंट एग्जीक्यूट की यानी कि चॉपस्टिक C2 को उसने पिक किया, और जैसे ही वो अपने राइट हैंड साइड वाली C3 को पिक करने लगा, फिलोसोफर P2 will get preempted, and P3 will also just pick the left hand side chopstick and it will again got preempted. And similarly P4 जैसे ही आया उसने भी सिर्फ फर्स्ट स्टेटमेंट को एग्जीक्यूट किया और क्या हो गया, वो भी प्रीएम्प्ट हो गया. सो भाई दिस इज the case, this is the worst case, that means all five philosophers come to eat. Now all are having only one chopstick with them, which is the chopstick, their left chopstick, but all of them requires their right chopstick. That means सभी फिलोसोफर के पास सिर्फ एक ही चॉपस्टिक है, विच इज देयर लेफ्ट चॉपस्टिक, एंड सभी को क्या चाहिए, राइट वाली चॉपस्टिक चाहिए ईटिंग स्टार्ट करने के लिए. सो इस पर्टिकुलर केस में अगर ऐसा केस आ जाए कि सारे फिलोसोफर वन बाय वन ईट करना चाहते हैं, लेकिन सिर्फ फर्स्ट स्टेटमेंट एग्जीक्यूट करके वो सेकंड स्टेटमेंट एग्जीक्यूट होने से पहले ही प्रीएम्प्ट हो जाए, यानी कि सभी फिलोसोफर्स के पास अपने लेफ्ट वाली चॉपस्टिक तो है लेकिन सभी को राइट वाली चॉपस्टिक चाहिए, तो भाई ये क्या केस है, दिस इज नोन एज डेडलॉक एंड दिस इज जस्ट बिकॉज ऑफ सर्कुलर वेट. तो भाई ये सारे फिलोसोफर क्या करेंगे, देखो P0 ने S0 की वैल्यू को 0 कर दिया, P1 ने S1 की वैल्यू को 0 किया, P2 ने S2 की वैल्यू को 0 किया बिकॉज उसने C2 को पिक किया है. फिलोसोफर P3 ने S3 की वैल्यू को 0 किया होगा, इसको एग्जीक्यूट किया है, और P4 ने S4 की वैल्यू को 0 किया. तो उसके बाद अगर सपोज फिर से यहाँ पे P0 आ जाए, वो ये वाली स्टेटमेंट को एग्जीक्यूट करेगा, तो उसको क्या चाहिए, चॉपस्टिक 1, उसको C1 चाहिए, लेकिन ऑलरेडी हमारे पास सारे सेमाफोर्स की वैल्यू 1 से 0 हो चुकी है, तो इनमें से कोई भी सेमाफोर एग्जीक्यूट नहीं होगा, कोई भी फिलोसोफर अपना राइट हैंड साइड वाला चॉपस्टिक नहीं पिक कर पाएगा. तो सारे के सारे ही फिलोसोफर यहाँ पे एक डेडलॉक सिचुएशन में फंस जाएंगे, कोई भी फिलोसोफर ईट नहीं कर पाएगा, एंड दिस पर्टिकुलर सिचुएशन इज नोन एज डेडलॉक. सो नेक्स्ट चैप्टर हमारा डेडलॉक का ही है. डेडलॉक को हम स्टार्ट करेंगे. डेडलॉक की डेफिनेशन ही यही है. यहाँ पे क्या है, सारे के सारे प्रोसेसेस ने एक रिसोर्स को होल्ड किया हुआ है, सभी के पास एक लेफ्ट साइड वाली चॉपस्टिक है और वो वेट कर रहे हैं दूसरे रिसोर्स की. सभी को दूसरा फॉर्क या चॉपस्टिक चाहिए, लेकिन जो उनको चाहिए वो किसी और ने होल्ड किया हुआ है, और वो वाला process भी किसी के लिए. So with this entire scenario is known as the deadlock problem, where one process is holding some resources and it is waiting for some other resources, and that particular resource is held by some other processes. तो भाई इस पर्टिकुलर P0 को C1 चाहिए, लेकिन C1 किसने होल्ड किया हुआ है, P1 ने. ये कब इसको रिलीज करेगा, जब इसे C2 मिल जाएगा, बट C2 ऑलरेडी किसने होल्ड किया हुआ है, P2 ने, एंड P2 रिक्वायर्स C3 व्हिच इज देयर विद P3, एंड P3 को क्या चाहिए, C4, लेकिन C4 किसने होल्ड किया हुआ है, P4 ने. तो ये सारे के सारे प्रोसेसेस ही अपना टास्क कंप्लीट नहीं कर पाएंगे. दिस इज नोन एज डेडलॉक सिचुएशन, एंड डेडलॉक की डेफिनेशन ही यही है. ये सारे प्रोसेसेस इन्होंने एक रिसोर्स तो होल्ड कर रखा है, सभी को एक रिसोर्स चाहिए, लेकिन जो रिसोर्स चाहिए वो किसने होल्ड कर रखा है, किसी और प्रोसेस ने होल्ड कर रखा है जो फर्दर किसी और रिसोर्स की वेट में है. सो दिस एंटायर सिनेरियो इज नोन एज द deadlock situation, and this is the overall problem which is known as the dining philosopher problem. So just let me discuss through slides the various possible solutions of this dining philosopher problem, and I hope the concept is very much clear, whatever I have explained you. Okay, so I hope the slide is now visible. So this is what the dining philosopher problem says, and this is the code. If any philosopher wants to eat, it has to pick the left chopstick, then right chopstick, then only it can start eating, and after eating the philosopher will put first left chopstick, then right chopstick, and then it will enter into the remainder section, which is known as the thinking section. Now there are some different solutions, because as you have seen, एक टाइम पर पांचों के पांच फिलोसोफर इकट्ठे ईट नहीं कर सकते. सो डिफरेंट पॉसिबिलिटीज क्या हैं फॉर दिस डाइनिंग फिलोसोफर्स प्रॉब्लम. सो देयर आर सम डिफरेंट सॉल्यूशंस प्रोवाइडेड बाय डिफरेंट पीपल. सो वन ऑफ द सॉल्यूशन इज दैट allow only 4 philosophers at the same time at the dining table to eat. So this is one of the possible solution. तो ऐसा क्या है, इस केस में हम किसी एक फिलोसोफर को बोल सकते हैं कि वो डाइनिंग टेबल से उठ के चला जाए, दैट विल डेफिनेटली सॉल्व द प्रॉब्लम बट नॉट कंप्लीटली। सो इस केस में भी अगर 4 फिलोसोफर्स भी होंगे तब भी simultaneously all the 4 philosophers will not be able to eat simultaneously, taking all the chopsticks. And another solution is allow the philosophers to pick up chopsticks only when both are available in a critical section. So this is another possible solution. तो हम इसमें फिलोसोफर को क्या बोल रहे हैं कि वो तभी पिक करे जब दोनों के दोनों अवेलेबल हो, बट यहाँ पे हम कंडीशन पहले क्या लगा रहे थे कि एक टाइम पर एक ही पिक होगा तो वो पहले लेफ्ट पिक करेगा फिर वो राइट पिक करेगा। तो अगर डेफिनेटली लेफ्ट वाला अवेलेबल है तो वो लेफ्ट पिक कर लेता है और राइट उसको मिले ना मिले तो वो फिर से वेट करने में चला जाता है नेक्स्ट अपने राइट चॉपस्टिक की। So this is also a possible solution, which is also known as all or nothing allocation of the critical resources. This thing we will discuss in detail in our deadlock chapter, which is our next chapter. And another solution is to use an asymmetric solution in which odd philosophers pick up their left chopstick first, and even philosophers pick up their right chopstick first. And you can just try to implement this thing also. तो भाई जिन भी फिलोसोफर्स का इंडेक्स ऑड है P0, P1 एंड P3 की बात करें तो वो अपना पहले लेफ्ट चॉपस्टिक पिक करें, और जिन फिलोसोफर्स का इवन इंडेक्स है P2 एंड P4 अगर वो अपना पहले राइट वाला chopstick pick करे, then there might be a solution to this dining philosopher problem. So you can just try to implement that also. So the question is, will this solution always work, and what will happen if we have an even number of philosophers? So in that particular case, क्या ये solution काम करेगा? So this is what you just have to try as your homework. So this is what all about